Now we'll get into two extra special conditions of rotational dynamics, a horizontal circle pendulum and then a bank road. So we know that this is going around in a circle like this, so there has to be centripetal acceleration, and it'll be pointing to the center of the circle. So how do we handle this? Well, straight down, of course, is going to be force gravity. Okay, and straight up is going to be a component of tension. Tension's going this way. And let's go ahead and complete our triangle like this. So the angle 30 degrees is here, and it's also here. We'll label this to be force tension here. This one will be force tension X. This one's force tension Y. And then we have force gravity pointing downwards like this. So it's force gravity. Now, since no motion is happening in the Y direction, we know that force tension Y has to equal force gravity. So here's my 30 degrees here, and I'm just going to label as theta here. So this is theta here. So then I really want to find force tension X, because force tension X is what is causing the net force in this example. And remember, the net force this time was just going to be the centripetal acceleration. So force centripetal is equal to then force tension, or force tension X. So how do I get that? Well, I can look at the tangent of theta, and that's going to be opposite over adjacent. So that'll equal force tension X divided by force tension Y. Okay, so but I know force tension Y equals mg. So solving for force tension X, I'm going to get mg tangent of theta. So I go over here, I know that mv squared divided by r is then going to equal mg tangent of theta. And then I can solve for velocity, how fast the ball will be going around in a circle, by rearranging my equation. It looks like m's will cross off. So it looks to be like v squared is going to equal then g tangent of theta, and let's put the r right there. Okay, and then r you might need to find using some trigonometry if I know the length of the string, or it might use the sign, or it might be given in the question, but that's how that system works. Now what about a banked road? So this is a car going in a circle on a bank road such that no friction is needed. So I'll put that up there so we don't forget. So no friction is needed to keep it going in a circle. It's all due to the banked road. Now, of course, if the angle is less than that, then some friction will be needed, but the banked road does help it go in a circle. So what forces do we have there? Well, we're going to have a force vector upwards, and of course a force vector downwards. We know these and have known these for a while. This one is force normal. Let's see, I'm trying to find a place to label it. I'll just put it up here off so it doesn't get confused. That's our force normal, and down here is force gravity. Okay, now in this case, force normal is not going to equal necessarily the force gravity y, because we're going around in a circle. But what we can do is break our force normal up into vector components. Okay, so we'll have this one going straight up. Okay, and this one going straight across this way. This would be force normal in the y direction. This is going to be force normal in the x direction. And whatever theta is here would also be my theta there. Okay, so force normal y and force gravity are going to be equal to each other. So force normal y is then going to equal mg. So we see we have a similar system as the other question. The tangent of the angle theta is going to be opposite over adjacent, so force normal x divided by force normal y, which is mg in this case. So I'll just put that there. So we know that force normal x is going to equal mg tangent of theta. Now, what purpose is force normal x providing? Well, the center of the circle is actually this way because this thing's rotating in a circle around. So force normal x is going to be equal to force centripetal. So then we've got mg tangent of theta is equal to mv squared divided by r. And again, m's are going to cross off. Okay, and depending what you want to solve for, I guess we can solve for, we'll say tangent of theta, okay, is equal to v squared over gr. So then we can figure out what angle we need to bank this road at, so that, and this would be the minimal angle that needs to be banked at, so that this car will go around a circle, okay, and we don't need any friction to keep it going in a circle. The force normal x takes care of all of it. So it's actually the same equation we derived in the above expression in the previous question, but we're solving for theta this time instead of v squared. So that's how we handle those two special cases of centripetal acceleration.